This video is intended to review some things we've been learning about functions. So remember that functions are simply a rule that tells us how to turn an input value, a number we put into a function, into an output value, the output that it spits out. We've been thinking of a function as a machine, where we drop a number in, and then there's a set of instructions, and we've been using the letter F as a shorthand to designate that set of instructions. And the instructions explain how to turn the input into an output. So if we were to look inside a function machine, those instructions might say to do things like add 8 to the number, and then multiply what you get after you've added 8, multiply that answer by 3, and then that's what it spits out. So the function rule is simply what goes on inside that function machine, and it's typically a set of mathematical operations. Now we want to keep track as we're putting numbers into a machine and getting numbers out of a function machine. We want to keep track of what we put in and what we get out. And there's a couple different ways we can do that. One is we can use a table. So we can simply have a column for the numbers we put in and a column for the numbers we get out. And each row in the table simply represents one input-output pair. So in this case, I put a 2 into the function machine, and I get out a 7. In the next row, I put in a 5, and I get out a 10. You can tell from looking that it appears as though the rule for this particular function is to add 4. Your tables can be vertical, like this, or horizontal, like what's shown down here. So in this case, x is the variable we use to track our input, and y is what we call our output. So in this one, I put in a -1, I put in a +1, I get out a -2. I put in a +2, I get out a -5. I put in a +3, I get out a -8, etc. So you can see that we can use tables to track what we put in and what we get out. And then once we've tracked that, we can make some inferences about the math that's going on inside of our function machine. Another way that we can keep track of what we put into our function machine and what we got out is with ordered pairs. Each ordered pair is simply one entry in a table. So this first ordered pair, -1, 2, that says that when I put a -1 into this function, I got a +2 out. I can plot that single point on the xy axis, where the x-coordinate is -1, and that stands for the number I put into my function machine, and the y-coordinate is +2, and that stands for the number that I got out. So each point on the coordinate axis has both an x and a y coordinate, and the x-coordinate tells you the number you put in, and the y-coordinate tells you the number you got out of a function machine. Another way that we can track what we put into a function machine and what we get out is through something called a mapping diagram. So in a mapping diagram, we put all of the inputs, all the numbers we're going to put into a function, in one box, and all of the outputs, all the numbers we get out, in another box. And then we draw lines to connect a particular input to a particular output. So in this case, the input 1 resulted in an output of 2, so we would draw a line from 1 to 2. Then we came along and we put a 2 into our function, and it spit out a 4. Next, we came along and we put in a 3 in our function, and it spit out a 6. So we're starting to have a sense of, I think I know what this function does. We put in a 4, and what do we predict we would get out? Well, at this point, you might predict you'd get an 8 out, and sure enough, you do. Then we come along and put a 5 into this function, and it turns out that 5 spits out the same output as as number 4 did. Both 4 and 5 spit out an output of 8. Now this function is a little bit weird, right? The pattern was consistent for the first 4 inputs, and then the pattern changed for the next one. This is a little bit weird, but it is still a function, because for each number that I put in, I only got one particular number out. When I put in a 3, the only number I got out was a 6. It's not like I ever came along a second time and put in a 3 and got something different out. So this is still a function. Another way we can track what we put in and get out of functions is through something called function notation. So let's translate from some words into some function notations. First, we would say that your score on a test is a function of how many questions you got right. If I tell you how many questions you got right, you can calculate the score. So your score on a test depends on how many questions you got right. The way we would write that using function notation is like this. Your score on a test is, that's what the equal sign means, is the same thing as a function of, that's f of, the number of questions you got right. So in this case, you would plug in the number of questions you got right, and the function would spit out your score. Another example, if you think about going to put gas in your car. When you're old enough to have a car, you're going to have to pay for gas to go in it. And the cost to fill your gas tank is a function of two different things. How much a gallon of gas costs, and how big your tank is. So the way that we would write this using function notation is we would say the cost to fill your tank is, that's our equal sign, a function of two things, the price per gallon of gas and the size of your tank in gallons. Oops, sorry, that should be tank, not kennel. We often write y as a function of x. Y, the output, depends on x, the input. And we would write that as y equals f of x. Y is a function of x. Y is something that depends on x. We also often use f for our function, but that's not the only letter we can use for a function. So if I wanted to say now y is a different function of x, there's a different set of rules for turning our input into our output, I could say y is g of x. F of x and g of x are two different function rules. They're two different sets of rules for turning an input into an output. So let's do some practice interpreting functions. In the previous slide, I used an example of a function that determines your grade based on the number of questions you got right on a test. So here's the specific function that does that for a particular test. Your score on the test is a function of the number of questions you got right. So in this case, x is going to stand for the number of questions that you got right. And the rule for turning the number of questions you got right into a percentage score is, first, take the number of questions you got right and divide it by 25. And then take the answer you got when you do that and multiply it by 100. This rule goes with a test that has 25 questions on it. So take a minute, pause this video, and write down in your notes, what does it mean if we say f of 25 equals 100? What does that go with in the real world story that has to do with getting questions right on a test and getting a score? Also explain, what does it mean to say that f of 20 equals 80? How do we interpret this little mathematical equation here in the context of the real world problem? Once you've written down what you think those two things mean, you can resume this video. Okay, so this first expression, f of 25 equals 100, well, 25 is the number we plugged in, and in this case, we were using that as the number of questions that we got right on the test. So this says the person got 25 questions right. The 100 is what the function spit out, and in this case, the function is spitting out the score on the test. So if you got 25 questions right, then you got 100% on the test. F of 20 equals 80, what does that mean? Well, our input was 20. That means if you got 20 questions right, then our output was 80. You got an 80% on the test. The next thing we want to try and understand when we look at a function is whether it's broken or whether it's just really weird. To be a function, it has to be reliable. Reliable means that a particular input, when I put a number in, I always get the same number out for that input. There's never a time when I put the same number in twice and I get two different things out, because that wouldn't be reliable then. So how can we tell whether a relation is a function by looking at tables? Well, in this first example here, we can see I put in a 1, I get out a 2. I put in a 3, I get out a 6. I put in a 4, I get out 8. Each input has exactly one output, so this is a function. In the second table, if I look across the top, I have 4 different inputs, and each one has its own output. Now I know that the output for the last input, when we put in a 5, we kind of expected that we would get out a 10 here, and we got an 11. This is weird, but it's not broken. This is a weird function, and I don't know exactly what the rule inside is, but I know that each input still only produced one output. Now let's look at this next table. Again, each input number goes with exactly one output number. It happens to be that the input 4 and the input 5 produce the same output. They both produce 8. But the key thing is that each time I put a number in, I know for sure what I'm going to get out. Now let's look at this last table. This one is not a function, and here's why. The first time I put in a 4, I got out an 8. The second time I put in a 4, I got out an 11. Now I'm really not sure what number this function is going to spit out the next time I come plug in a 4. This is not reliable. This is broken. These two functions are weird, but this one is broken. We can see the same thing when we look at function maps. These are the same 4 relations as were on the previous slide. Notice that when we use function maps, if we have a relation that's not a function, like this last one here shown in yellow, the input of 4 has 2 different outputs. It has 2 different arrows coming out of it. When I put in a 4, I don't know whether I'm going to get an 8 or an 11 out. The domain is the numbers that we are allowed to put into a function. So let's think about some reasons that we might not be allowed to plug some numbers into a particular function. One reason that numbers might not be in the domain, might not be allowed into a function, is that they'd break the function. For example, if our function asks us to take the square root of a number and we plug in negative numbers for there, you can't take the square root of a negative number. So in this case, our domain, the numbers we're allowed to plug in for x, are all numbers greater than or equal to 0. We can plug 0 into this function, and we can plug positive numbers into this function, but we can't plug negative numbers in. Now let's look at a different function. 1 divided by x. 1 over x is the same thing as 1 divided by x. In this case, the one number we're not allowed to plug in is 0, because you are not allowed to divide by 0. Bad things happen when you try and do that. So in this case, the domain, the numbers we're allowed to plug in, are everything except 0. So for this one, we would say the domain is all real numbers except 0. X cannot be 0. That's the number we're not allowed to plug in there. All right, what are some other reasons that numbers might be restricted from the domain? Well, some numbers might not make sense in the context of a problem. For example, if you have a function that tells you how high the ball is off the ground after it's been in the air for a certain period of time, in this case, the variable you're plugging in is the time that the ball has been in the air. We don't go backwards in time. We don't have negative time. So it's only reasonable to plug in numbers that are greater than or equal to 0 for time. Imagine we have a stopwatch. The initial value on the stopwatch is 0. We click it, and the numbers go up from there. Time starts at 0 and moves forward. Sometimes a domain is artificially restricted. That means, like, we don't really know why, but for some reason some person came along and said, hey, you're only allowed to plug in x is greater than or equal to 1 into this function. You may encounter problems where a domain has been specified to be a particular number, and that's fine. Like, we don't need to see into the mind of the person who said, for the purposes of this math problem, we're restricting the domain, but it might have been that someone artificially restricted it. The range is simply the numbers that you get out of a function. So again, there's some reasons that numbers might not be in the range. For example, some functions won't spit out particular numbers no matter what you put in. If we have an absolute value function, y equals the absolute value of x, no matter what number I plug in here, this is never going to spit out a negative number. Whether you plug in a positive number or a negative number, when you take the absolute value of it, it gets rid of that negative sign if it was there. So if I plug in negative 2, this function spits out positive 2. If I plug in positive 2, this function still spits out positive 2. In this case, the numbers that I get out of this function are always going to be positive. They're going to be greater than or equal to 0. Another reason that the range might be limited is that the domain got limited. So if I have a simple function like take the input and add 1, but if I limit the domain, if I say the only numbers I'm going to plug in are numbers greater than 3, well, if I plug in 3 to this function, 3 plus 1 is 4, the numbers I'm going to get out are going to be greater than 4. And the reason in this case that the range is limited is because I restricted the domain. I said you're only allowed to plug in numbers greater than 3, so in this case you're only going to get out numbers greater than 4. Last, let's take a look at intervals. So an interval is just a section of graph between two different x values. So this is a really weird looking graph here. Let's look at some intervals. So what's shaded here is the interval between x equals 1 and x equals 3. Let's see, I actually made that x equals 1 and x equals 4. Let's fix that. X equals 1, 2, 3. There we go. Now this is the interval between x equals 1 and x equals 3. So this is x equals 1. I went over to 1 on the x-axis. Here's x equals 2. Here's x equals 3. So I shaded over everything that has an x-coordinate between 1 and 3. And on the graph, from here down to here, that's the interval on the graph between 1 and 3. This is the interval where x is between -3 and 0. Notice the notation here. I have the number x, and I'm showing that it's greater than -3, but less than 0. It's between -3 and 0. So on the graph, from here to here, and then up to here, this is the interval on the graph from -3 up to 0. I can look at a graph and I might ask you, what are all the intervals where the function is increasing? So I've shaded here all of the intervals on this graph where the function itself, that is the black line here, is increasing, where the function is going up as we go from left to right. So this is the first interval where the function is increasing. It looks like it starts at x equals -1, 2, 3, 4, 5. So this is the interval from -5 up to -3. This interval here, the function is increasing. Our next interval where the function is increasing is from -1 to +1. As we go from -1 to +1 on the x-axis, our function is increasing as we go left to right. And then we have another interval over here. This is the interval from x equals 1, 2, 3, 4. So this is from x equals 4 to x equals 5. And again, we can see in that interval, our function is increasing. So what you're going to do next is you're going to briefly read through the next few pages in your packet. When you get to page 9, there's some practice problems that involve domain and range and intervals. You're going to work through those and then we'll come back together.